Hey, Debbie, can you see and hear us tonight?
Yeah, if you're in the 3 o'clock showing, I don't think I could go to sleep and then wake up with ghosts either.
Hello, Debbie, can you hear me?
Like I have to stay up.
Hey, there's Mike.
I hear you, bud.
Would you do me a favor? Would you, never mind, it just came in. I was going to get you to reshare, and it just came in.
The problem, the computer was like sleeping.
Okay, cool. All right, we are looking good on our end, ready to go whenever you are.
Excellent. What I want to start with tonight is right here. This is number 3 on the capstone project. We did the first 2, right? We talked about them already. So the third one is, problem 3 is the gender versus the age. Question 2 asks, what's your gender, female, male, or other. Question 4 asks you, what was your age score? Remember the number of adverse childhood experiences. It says, create a suitable graph to display the distribution of gender and gender alone. Well, gender is categorical, right? So I would like to make a bar chart. Now, the reason I'm showing you this is, I know you know how to make a bar chart, but every time you made one for one of the homework problems, or I made one in class, you remember I always came in here and changed this to values from a table? Because remember, the way all the data was always given to me up until now was I always had a table, I had the categories listed, and I had to count a percent. I don't have that this time. So I got countless of unique values. What that means is you have the raw data. Nothing's been summarized for you. So leave that alone. We want a simple one, and I want it for gender. I'm going to click OK. And what this is going to give me is it's going to give me the count that picked each one, right? Female, male, or the other. Yes? So that's the guy you need over here to copy and paste for the distribution of gender. It says, what is the mode of this distribution? Now look, I've probably never mentioned the mode by itself all semester. The mode is the one that is the most frequent, the one that was chosen the most often, whichever way you want to think about it. So if I look here, which one is the most frequent? Obviously, it's the category that has the most individuals in it, yes? Okay. I can get rid of that guy. If I come back here, it says create a side-by-side box plot to display the, typo. That shouldn't be age. That should be the ACE score of students for the different levels of gender. Look, I've got, what I want to do is I want to compare the ACE score for females, males, and other, right? So this is a job for a side-by-side box plot. And so I want to come here, and I want to make a box plot. Remember, that's graph, box plot. I don't want a single box plot. I'm going to end up with 3 on the same graph, one for the females, one for the males, and one for the other. So I want this with groups. What do I want box plots of? ACE, right? They're ACE scores. I want to see the distribution, or I really want to see the 5-number summary, right? That's what the box plot's going to show me. And then, how do I want them? I want them by their gender. Everybody okay with that? So I chose box plot, multiple ones, right? The one there on the second one. ACE is the variable you want to graph, okay? And then the categorical variable is gender. That should be what you're looking at. That's the graph you need. That's your side-by-side box plots for to display the. And I apologize. That was sent to me, and I didn't catch that because all the big bold print was correct. I didn't actually read word. Yeah. You want your ACE score, not your age. Okay? So it says, use the side-by-side box plot to answer, found in part C to answer the following question. Which gender has the largest variability in terms of their ACE score? Which one's got the largest variability? It's the one with the biggest spread, right? I'm going to give you the one with the largest box. That's the way I'm going to think about it. I don't want to think about the outliers and stuff. I want to think about the one that has the largest box. Okay? Which gender has the highest median ACE score? The median is the line that's in the middle. Now notice, the one for the males, you don't see any line in the middle of that box anywhere, do you? But remember, if I hover here, what this is going to tell me is the median and the first quartile are the exact same value. Right? Okay. Which one has the highest median score? I'm sorry, I just can't say it out loud. Other? I couldn't help what else there is. Which gender has the largest IQR in terms of their ACE score? Which one's got the largest box? Hey, is it possible all 3 of them are the same answer? No. And then it finally says, discuss 2 or more complete sentences what this plot tells you. Well, one of the things I see is the female and the males, they got outliers, right? No outliers in the other. The other one looks like it'd be roughly symmetric. The other 2 look like they're a little bit skewed to the right, right? Because remember, the median is closer to the first and the third than the females and the males. You want to say something about that. But overall, what do we see about the ACE score? Which group has the highest ACE score on average? Other. The males have the smallest variability. I'm just picking out little things I can say here, right? And I'm just looking for 2 things. And I guess the big thought I have is that, you know, in the big picture thinking here, it appears like the other have, on average, a higher ACE score than the females or the males. Okay? Why am I saying that? Did you notice how these other 2 boxes are down here, and the one for the other is a little bit higher? The males and the females are about the same, other than the fact that the males having a smaller variability, smaller spread. And that should take care of that problem for us, shouldn't it? So then on Tuesday, we'll talk about our regression problem. You know, our, whatever chapter that is, chapters 4 and 5, we'll talk about this one. Where that leaves me and you on where I left off, what's the date? Last Thursday? Was this. We were looking at, I want to remind you where we're at before I work a problem. I'm looking for a confidence interval for mu. Right? So what I'm doing is I'm wanting to estimate a population mean mu, that's my parameter. Right? And what I really want is a level C confidence interval. Remember, we always start with this success rate. Okay? Now, I'm going to come over here and put in parentheses. I know it doesn't, you know, you're going, why do you always keep doing that to me? Well, you'll see in next week sometime. You know, I keep reminding you, look, you were given sigma somewhere in the problem here, right? The standard deviation was given to you. And then my calculation, my formula looks like this. Remember, you're going to use x bar as your estimate, that's your statistic. And then it's plus or minus z star. Remember, the z star comes from the confidence level. It tells you how many standard deviations you need to go on either side of the mean to capture the C percent from the level of C confidence interval. Sigma times the square root of n. That is your confidence interval to estimate a population mean mu when you are given the population standard deviation sigma. You notice there's 4 things we have to be able to do this. Sigma will be given to you in the problem. N is your sample size. The z star comes from the confidence level. And then your x bar, your sample mean, your statistic here, will either be given outright to you in the problem, or they'll give you the data and you've got to find the average. All right? Other than that, it's just let's plug in and go. So what I was thinking is this. I'm not overly concerned on page 383 about confidence intervals, the 4-step process. I kind of do my own little thing here. And what I would like to look at is, I want to look at problem 16.6, and I'm going to need some of your help. 16.6 on page 384. I don't want to do the example that's in the book. Now you can see what they did. So I'm going to pick a problem here and show you how I read, how I pull stuff out. It says, measuring melting point. The National Institute of Standards and Technology, the NIST, supplies standard materials whose physical properties are supposed to be known. For example, you can buy from the NIST a copper sample whose melting point is certified to be at 1,084.80 degrees Celsius. Of course, no measurement is exactly correct. The NIST knows the variability of its measurements very well, so it's quite realistic to assume that the population of all measurements of the same sample has a normal distribution. Why did I label that 2? Remember my simple conditions? 1's SRS, 2's the population distribution is normal, 3 is signal given to me. And it says with mean mu equal to the true melting point, and sigma is equal to 0.25. Right, so that's number 3. Sigma is supposed to be given to me. What's number 1? Now, they're telling me this is true, and they're telling me that's true. It says, here are 6 measurements on the same copper sample, which is supposed to have a melting point of 1,084.8 degrees Celsius. I've got 6 pieces of data here. So I've got a sample of size 6, right? Will somebody, while you're sitting there and I'm reading, will somebody tell me what x bar is? See, they didn't actually give it to me. They gave me 6 different measurements, and I need to add those 6 together and divide by 6 to tell me what my average over those 6 are. And then it says the NIST wants to give the buyer of this copper sample a 95% confidence interval for the true melting point. Look, C is equal to 90%. Mu is the true melting point that we are trying to estimate. It says, what is the interval? Okay, let me ask you this. I know what chapter, you know what chapter we're in. You know we only know one confidence interval, but here's the thing. I'm going to circle this. That is given to me. So then when I start fumbling through my little formula sheets, I'm looking for this guy right here. That's the guy I'm looking for, right? Because that's the one I use when I'm given sigma and I'm trying to estimate a mean mu. Now, did anybody figure out what X bar was? 1085.13. So look, I'm going to underline a couple things. We know this. That's given to me. I know what my sample size is. Where does Z star come from? Z star is coming from table C. And Z star, coming from table C for 90% confidence is oh shit, I'm in the back of the book looking at table C, right? And I'm on page 699. I go to the bottom, Z star. I'm looking up the column that's 90%. When I read all the way across and read Z star, I get 1.645. Table C. I'm looking at 90% confidence. 90% confidence, Z star is 1.645, right? That's where I'm reading that from. So, are we ready to plug in? Yeah, I got X bar. Somebody calculated that for us from the data. My X bar is 1.1085 0.13 plus or minus 1.645. Your standard deviation is 0.25 and your sample size is 6. Now, here's the thing. When I work one of these confidence intervals, I work from right to left. And you're like, really? Yeah, I work from right to left. In other words, what I want to know is, I'm going to write down my X bar again, plus or minus. I want you to take 0.25, divide by the square root of 6. And then I want you to multiply by 1.645. See, I want this to look like my estimate plus or minus my margin of error here, right? So what you get, 0.25 divided by the square root of 6 times 1.645. Yeah, we're going to have a bunch of decimals here. What do you got? Point what? No. I want the whole thing together, right? I want all this together. I want the 0.25 divided by the square root of 6 times the 1.645. The reason I like it like that, because this looks like an estimate plus or minus your margin of error. And look, the problem may have just asked you for the freaking margin of error, the plus or minus part. Okay? Now, at this point, we've got to do each piece. I can't do it all at once, so I think about 1085.13 plus 0.17, 1085 plus 0.13 minus 0.17. I can do this one. This one's 1085.30. This one here is 1084.96. There is your confidence interval. And what I mean is, two ways to write it. The confidence interval is from 1084.96 to 1085.30. Another way to write it is in interval notation. The math guy in me comes out. Right, so 1,084.96 to the 1,085.3. That is your 90% confidence interval. One more time. How did I get all my little pieces? The confidence level was given to you. Z star is coming from table C. The sample size was given to me. Sigma was given to me. The X bar, the data was given to me. We had to add them together and divide by 6. Right? And so then I'm plugging in. Now, I'm not done. I know this problem just wanted the confidence interval. I understand that. But I try to be very consistent with you because I don't know how the answers will, if they'll be asking for just that or the next step. We are 90% confident that the true melting point mu is between 1,084.96 and 1,085.32. Notice what I'm giving you here. I'm giving you our success rate to confidence level. I'm telling you what you're trying to estimate, and I'm giving you the interval that we calculate. I'm not telling you that mu is in there. I'm telling you, with 90% confidence, the true melting point mu is between here. I'm giving you the success rate, I'm telling you what you're trying to estimate, and I'm giving you the interval. That's a pretty standard looking statement here, right? That's the one I gave you last Thursday, right? Or what I've got underlined is what changes. If I want 95% or whatever it is, that's what I'll put in there. I want everybody to know the success rate of my method here. Now, this whole problem, there wasn't nothing ever stopping me from calculating anything here, right? As long as I can find X bar, Z star, sigma, and N. What's the one piece missing here? Nowhere did I see, let's assume this is a random sample or any of that stuff, yes? So should I take all this with a grain of salt? Hey, what happens if it had been some kind of voluntary response or some bad sampling design? How do you feel? I don't feel too good. My point is, nothing stops you. Whether you're looking at a simple random sample or not, as long as you got all the numbers, you can calculate. Nobody told me it was a simple random sample, so in the back of my head, I'm thinking a little bit about, look, you never even told me random sample in the problem. Keep that in mind. Okay? Now, here's my thing. I don't see standing here and calculating 10 of these. Right? As long as you're listening to what I'm telling you about where things come from, and then where I'm plugging in, I don't see a problem because I'm not memorizing the formula. And what I'm talking about is that formula right there. I'm not memorizing my Z star. Hell, I've got table C with me all the time. What's the important thing here? You see what I got circled in blue? I needed to know the standard deviation, and I was trying to estimate a population mean mu, whatever in the hell it is. All right? With that said, I got one other thought about all this confidence interval stuff. How confidence interval behave. And what I mean is this. The margin of error in our confidence interval. I'm going to use a little m for the margin of error, and I'll be consistent with you all the way through the semester. Every time I do a confidence interval with a margin of error, I'm going to call it m. Remember, it is the plus or minus part. Right? Remember, it's x bar plus or minus your margin of error. That's your margin of error. Z star times sigma over the square root of n. Well, what people want to be able to do, and what they mean about how does a confidence interval behave, is how does the margin of error behave? And what we're thinking is, I want to make m smaller. See, here's my thought. X bar is your estimate. It is dead in the middle of your confidence interval, and then you add the margin of error and you subtract the margin of error. We would like the margin of error to be small, right? Because then the width of my interval is smaller. So what can we do to make m smaller, to make your margin of error smaller, the width of your interval smaller? Well, to me, I've got two thoughts. One is less confidence. Maybe that's not the right word. Maybe I should say we decrease the confidence level. Not a perfect idea, but it's an idea. In other words, instead of calculating at a 95% confidence level, let's do it at 90. Or if you started at 99 and you want to make your interval smaller, let's go 95. You do understand that the larger my confidence level, the larger my interval has got to be, because, you know, if I'm freaking 99% in shorts in there, my interval is going to have to be larger. Well, what does this actually do when I say decrease the confidence level or settle for less confidence? What does that do to the Z star? Z star gets smaller. And now, we've got to have a little bit of what I want to call number sense. And what I mean is this. You see that formula right there? Z star times sigma over the square root of n. If your Z star gets smaller and you're multiplying by it, doesn't the whole quantity get smaller? In other words, instead of multiplying by 95% confidence, Z star being 1.96, you're willing to settle for 90% and multiply by 1.645. Which one makes the smaller number? Multiplying by 1.645, right? Because you're multiplying by the Z star, multiplying by a smaller Z star will make the margin of error smaller. And I'm sorry, my hands do this because the margin of error is setting the width of your interval. Okay? One other way that I see that we can make m smaller increase sample size n. Now, why does increasing the sample size make it smaller? Well, you're dividing by the sample size. So when you divide by a larger number, you make the whole quantity smaller, right? So again, that's that number sense. If you multiply by a smaller number, you make the whole quantity smaller. If you divide by a larger number, you make the whole quantity smaller. So if you'll increase the sample size, that will also decrease the margin of error. Hell, think about it. A long time ago, I told you larger samples give you more accurate results. There it is again. Right? You give me a larger sample than what you started with, you're going to decrease your margin of error. You're going to be more accurate at the exact same confidence level. Okay? The book's going to give you a third one, but I'm giving you the two that I have my hands on. You know, I can change your sample size. I can change your confidence level. And I'm all thinking about, okay, what does it mean? If you're dividing by n, you divide by a larger number, you make the margin of error smaller. If you're multiplying by Z star, if you multiply by a smaller number, decrease the confidence level, you will decrease the margin of error. That's my thought. I got one more little thought here. To cut m in half. So whatever margin of error, with whatever sample size and whatever confidence level you're working at, to cut that margin of error in half, you need 4 times the sample size. Why is it 4? What's the square root of 4? Well, in my little world, the square root of 4 is 2. You see, if you started out with n being 100, and you went to 400, 4 times 100, you take the square root of 4, you get 2 times the square root of 100, you just cut everything, you just divided everything by 2, right? So it's not like you want to cut it in half, you take twice the sample size. No, because the sample size is in the square root, you need 4 times the sample size, so when you take the square root of 4, there'll be a 2 pop out in front there, and you'll be dividing by 2, okay? Now, I would like to do this just to get us a little practice here, messing with some more confidence intervals. And there's 2 different problems. On page 386 and 387, there's a problem 16.8 and there's a problem 16.9. One of them is, let's start messing with the confidence level and see what happens. And then the other one is, let's start messing with the sample size and see what happens. And so I want to look at 16.9. on page 387. And then before I do that, can I come back here just a second? You see this part right here? I always write it in terms of that because that's my idea, is to make the margin of error smaller, right? So I get closer to my x bar. You understand, if we wanted to make the margin of error larger for whatever crazy reason, we would do the opposite, right? You would increase the confidence level. Or you would decrease your sample size, right? It goes both directions. If you want to make them smaller, less confidence, larger sample size. If you want to make margin of error larger for whatever crazy reason, you would decrease the sample size and increase the confidence level, right? I always give it to the students in terms of making the margin of error smaller because that's what the hell I want to do, okay? Now, 16.9, sample size and margin of error. Example 16.1 on page 377 describe the NHANE survey data on the body mass BMI of 654 young women. The mean BMI in the sample was X bar is equal to 26.8. They're also telling me that N was 654 there. Off to the side, they're telling me you got a simple random sample, that the population distribution is normal, and that sigma was 7.5. I like all 3 of these things. We like that, we need that, and we need that. Right? That's all that third line there. And so, what we've got is this. It says, suppose, just for the sake of things, that we had an SRS of 100 young women, what would be the margin of error for 95% confidence? So part A says, instead of having 654, let's say we had 100, what would be my margin of error? What's the formula for my margin of error? I'm going to do it like this. My confidence level is 95%. Table C is going to give you Z star is 1.96. Right? So what's my margin of error here? Plug in what you've got. Z star is 1.96. Sigma is 7.5. The square root of 100. What do I get for my calculation here? 7.5 divided by 10 times 1.96 is going to give me a margin of error. What do you get? So if your sample size had been 100, your margin of error would be 1.47. Now, can I come up with a confidence interval? Yeah, I'm going to take 26.8 plus or minus 1.47 and go both ways. That's not the point of this problem. They just wanted the margin of error. Part B. Find the margin of errors for 95% confidence. Z star is still 1.96, but this time we want to say, suppose we had a simple random sample of 400. So what's my margin of error? 1.96 times 7.5 all over the square root of 400. Your margin of error is going to be point. And you're going to do. Last time you were struggling, you didn't have a calculator. Why did you have to have her do 1.47? But now all of a sudden, can you look and tell me that's 0.735? To cut the margin of error in half, you need 4 times the sample size. I went from 100 to 400, so that means I'm going to cut the margin of error in half, right? That's how I achieve it. It also wants to know, suppose you had a sample, an SRS of 1600. What would your margin of error been? 1.96, 7.5, all over the square root of 1600. You frown. Your eyebrows raised it. I got the right answer. You know how?
Yeah.
I cut in half again, right? I went 4 more times whatever I had. I needed the first one because I didn't know I didn't know the first one for 100 was 1.47. Then I went to 400. That means I had 4 times the sample size. Well, again, I went 4 times the sample size, so I cut it in half again in my head. The point is this. This is supposed to illustrate something to you. If I start increasing your sample size, what happens to your margin of error? That's what Part C is going to ask me here. Part C is going to say, all right, compare the 3 margins of error. Well, when n was 100, I had 1.47. When n was 400, my margin of error was 0.735. When n was 1600, my margin of error is 0.3675. It says, how does increasing the sample size change the margin of error of a confidence level? A confidence interval with the confidence level and population standard deviation means the same. If you increase sample size n, the margin of error m does what? It decreases. That's putting numbers to what I was telling you on the previous page about the sample size. If you're going to increase your sample size, you will decrease your margin of error. The fact that they went from 100 to 400 to 1600, they were just making my life easy where I only needed the calculator 1 time. Nothing else special about that. All right, one more time. Okay? In this chapter, okay, there's 2 things you've got to be able to do. I want to remind you of these simple conditions because there's nothing stopping me if I got the numbers from calculating your confidence interval. We always need a simple random sample. We need our population distribution is normal. And I always give you number 3. Sigma is given. Somewhere in the problem, they need to tell me the standard deviation of the population distribution. All right? That's what has to happen. I'm going to give you, obviously, mu is unknown. If mu was not unknown, we would not be trying to calculate a confidence interval to estimate it. And then my level C, confidence interval for estimating a population mean mu. I keep writing it like you're going to memorize it. You don't have to. It's on the formula sheets. All right. The only other thing I can think about is that your margin of error is the plus or minus part. How do I make it smaller? Increase your sample size or decrease your confidence level? Now look, I know I talked to you last Thursday about this. I talked to you about this for like freaking 25 minutes here. That's what you got to be able to do. If I'm going to do this part, or even the other part, if I'm going to do this, will everything be in the problem for me? Will the sample size be there? Yeah. Will the standard deviation sigma be there? Yeah. Will Z star be in the problem? No. What will be in the problem is the capital C, the confidence level will be there. You'll look Z star up. What about X bar? Will X bar be there? It's possible. If it's not there, the data will be there, and you can figure out what X bar is. I actually want to ask you the same thing about, okay, so maybe the problem just asked me to calculate the margin of error like that problem 16.9 that me and you did. Will sigma be there? Yeah. Will the sample size be there? Yeah. Where Z star comes from? It comes from the confidence level. I got nothing in it. That's it. And then, you remember this little statement back here? Please pay attention to this part. We are 90% confident. We're level C confident that the mu that you're trying to estimate is between or in the interval that you calculate. That's the other thing to be able to do. Make that statement. Okay? Now, here's the deal. We're ready for the next chapter. The next chapter is an exciting one. I'm sorry. I'm just smiling with myself. It's our other inference method. So this one here, the title of it is Tests of Significance. And I'm going to give you, obviously, it's going to be called the basics. And it's called the basics because sigma is going to be given to you. Now, you know those simple conditions I just wrote on the previous page? Those right there? These are good for chapter 16 and chapter 17. Both chapters. Those are your simple conditions. Okay? Now, I got to write this part down for you. The goal of a test of significance is not to estimate anything. The goal is to assess the evidence provided by the data Well, what are we going to do with the data? We're going to calculate an X bar, right? So when you say to assess the evidence provided by the data by your X bar, by your statistic, about some claim concerning a population parameter. In this chapter, your population parameter is mu. So if you take out the X bar and you take out the mu, we're talking about just test of significance in general. But in this chapter, the data is going to give you my X bar. The population parameter is going to be a mu that we're going to make claims about. Now, here's the deal. I'm going to talk to you about example 17.1 and see if I can get you to think about a test of significance without me using any other language, without me writing anything down. It's just this. And I'm not going to put it in terms of a mu and an x bar. I'm going to give it to you just something that we can talk about here. And I'm going to use this example 17.1 and myself as the example. All right? Here's the deal. It turns out I'm a hell of a basketball free throw shooter. Right? When I played, I made 80% of all the ones I ever took. Now, did I make a claim about something? Yeah. Now, it's not a population mean, but I made a claim that, all the free throws I would ever shoot, I would make 80% of them, yes? And so you guys are all looking at me going, dude, you're kind of old. I don't really believe that. You don't look like you was a basketball player. I don't really think you could do that now. So let's go downstairs to the gym. And dude, we'll get you a basketball, and you shoot 20 of them. We'll see how many you make. Right? So if I make the claim that I make 80% of them, and we go downstairs and we shoot 20, I shoot 20, how many are you expecting me to make? Does anybody have 16 pop into the head here? 20 times 0.8, 20 times my percentage? You're expecting me to make 16. Now, obviously, if we go downstairs and I only do it one time, you're not expecting me to make exactly 16. You're expecting me to make 16 on the average, right? If we do this like 10 times in a row, you're expecting me, if I average all the ones up I made, you're expecting me to average around 16, correct? Okay. I just made a claim about a population parameter, the percentage of free throws I make, right? I claimed I made 80%. Now you're testing me. Here comes the data. We're going to go downstairs. We're going to shoot 20 of them. I'm going to shoot 20 of them. All right? Let's say I make 15. How do you feel about my claim? Did you check in your head? Yes? Thank you. Well, hell, it's pretty close to the 16 you was expecting me to make, right? What about if I make 17? Oh, what about if I make 16? Well, shit, that was exactly what you were expecting. What about if I make 12? Yeah, I got my head nodding his head back there. What about if I make 5? You're like, dude, you lied to me. Why is that? Because what actually happened when we did this is so far away from what you was expecting to happen, there has to be something wrong, right? Well, what's wrong? It's not the 20 I shot. What's wrong is the claim I make, right? I don't actually make 80%. I actually make something less than 80%. Yes? See, here's the deal. We make a claim, and then we collect data, like shooting free throws, to see what you believe about that claim. Is the data consistent with that claim? Now, I'm giving you some little test of significance language here. When I say it's consistent, that's when I make 17, 16, 15, and maybe even 14, right? Pretty close to the 16 we were expecting. When there's something wrong and there's something up with what I was claiming was when I made 4, or 5, or 3. You were expecting 16. Am I a long way away from that? And the answer is yes. That is our first test of significance. Without me writing a word down, any language, nothing. The catch about all this is the test of significance has an elaborate vocabulary. I'm writing that like that's not true about every chapter we talk about, but the vocabulary here is very elaborate. Now, I promised you something at the beginning of chapter 16 that I wouldn't show you anything new, right? I didn't show you anything new at the confidence interval. That calculation we came up with was all dealing with the sampling distribution. Same thing here. Any calculation I'm going to show you here, you've already seen, and you've already done. So, here's the way all this works. To put some numbers to all my talking here, the reasoning of tests of significance. Rob, my friend's not there alone, is she? Oh, thank you for being there tonight. No, they wanted to get the test score better. Okay? Now, all of this is working off the sampling distribution of X bar. You know, the guy we've looked at, you know, we know that if the central limit theorem says if the sample size is large enough, it's approximately normal with the mean, mu, sigma over square root of standard deviation. It's that same guy. Okay? Now, I want to look at this example 17.2. We're going to work through this example. And then what we're going to do is, look, no problem have me and you worked all semester that it takes so many pieces to get there. Well, a test of significance, to be honest with you, it takes 4 steps and sometimes a 5th. All right? So I'm going to work through this whole thing, and then what's going to happen is we're going to come back and we're going to talk about each little piece of this test of significance by itself. All right? So this example 17.2 says this. Diet colas use artificial sweeteners to avoid sugar. These sweeteners gradually lose their sweetness over time. Manufacturers therefore test new colas for loss of sweetness before marketing them. Trained tasters sift the cola along with the drinks of standard sweetness and score the cola on a sweetness score of 1 to 10. Obviously, the larger the score, the higher the sweetness, right? You score to 10, that's as sweet as it gets to you, right? 1, not sweet to you, okay? It says, the cola is then stored for a month at high temperature to imitate the effect of 4 months storage at room temperature. Each taster scores the cola after storage. So each taster is given it a score before and a score after on a scale of 1 to 10, 10 being the sweetest. All right? It says this is a matched pairs experiment. Oh, damn, they pulled shit out of chapter whatever that was. It's a matched pairs where you're looking at before and after. Right? Each person is actually a pair, and then they're going to score it before, they're going to score it for a month of high temperature, they're going to score it again. That's definitely matched pairs. Okay? And it says that it's the data is the differences. Hey, anytime I see matched pairs, and you'll see me do this the rest of the semester, I'm thinking about how did you do the subtraction. And it's the score before minus the score after school. The reason that's important to me, because if you scored a 7 before and you scored a 3 after, then your difference is a 4, right? If you scored a 5 before and a 7 after, then your score is actually a -2, yes? See, here's the thing. Positive differences mean you think the cola lost sweetness, yes? Negative differences means, for whatever reason, you think the cola actually gained sweetness after scoring, yes? And if you scored it the same, a 4 and a 4, your score would be a 0, and that means you think it tasted exactly the same before as it did after, right? Okay? Now, it says, the bigger these differences, the bigger the loss of sweetness. Suppose we know for any cola, the sweetness loss scores vary from taster to taster according to the normal distribution. You know why I'm numbering 1, 2, 3? Here's your simple conditions. It's saying the population distribution is normal. We're looking at anybody that would ever do this experiment. All the possible tasters, right? They're telling you that their differences, whatever their score is before minus after, follow a normal distribution. And the standard deviation is sigma is equal to 1. Anybody see simple random sample? It won't be. But the reason I'm going to write it and I'm going to check it is matched pairs. Something was done in a random fashion, right? So everything here, all my little conditions are met rather nicely here. Okay? And then we keep reading. It says the mean mu for tasters measures the loss of sweetness is different for different colas. Mu is the mean loss of sweetness for all tasters. That's the population you're looking at. We don't know this mean mu, right? It says, here are the sweetness losses for a cola currently on the market as measured by 10 trained tasters. There was 10 people that participated in this matched pairs experiment. N is equal to 10. The first person had a 1.6 difference, 0.4, 0.5, minus 2.0. I'm just reading the data for you. It says the average sweetness loss given by the sample mean is. Everybody know how they did that? They add those 10 numbers up, divided by 10. They got the average, your statistic being 0.3 here, right? Remember, this is your sample mean. They took the average over the 10. This is your statistic. It says, on average, the 10 trained tasters found a small sweetness loss on average. Why is that? Because it's positive, right? So on the average of those 10, the average came back to be positive. Remember, I told you positive means it lost sweetness, yes? The weird thing is when I look at the 10, somebody had 1.6, 0.4, 0.5. The first three actually lost things that lost sweetness. What about the negative numbers? Those are the ones that actually think gain sweetness, right? So some of them are positive, some are negative. The average over the 10 is 0.3. Okay? I'm still not at the punchline yet. Are these data, I'm reading the very last line in this example, are these data good evidence that the cola lost sweetness? Now, what color would you like for me to use here so that when you see this, you know what they're asking you to do? Nobody says it doesn't say do a test of significance. It says, and the magic words are, good evidence means and you got to be wondering why that makes a difference. Well, I'm trying to keep things separate for you. When you're trying to estimate something, we know confidence interval. When we are looking for good evidence of whatever in the hell it is, I don't even care what it is yet. You're asking me about good evidence. They're asking you for a test of significance here. Okay? Now, with all that said, it says, are these data good evidence that the cola lost sweetness? So, I want good evidence, means test of significance, that it lost, the cola lost sweetness. That's what you're seeking evidence for based off of these 10 tasters, off of this X bar. Now, the way all this works is we're going to make a claim. Mu, remember, mu is the mean loss for all tasters, that mean difference, mu. We're going to make a claim about mean, about the mean mu, and ask if the data X bar gives evidence against it. Now, every problem I've done for you, every problem I've asked you to do all semester, we always attack it head on. You know, it says do this, help me, and you just do it, right? It doesn't matter what chapter we were in, the problem said do this or do that, calculate this, do this. It's like we just got freaking blinders on and we just attack it and we just do it, right? Until now. The reason I got two underlines under that against is we gotta kind of attack this from behind. Look, if I was sitting at home, I'm going to tell you that, I would like to go ahead, straight ahead, but if I was sitting at home, I'd tell you, we're kind of going to go at this ass backwards. Start. Right? It's the only time I'm going to do it to you is we do a test of significance, and I can break it down to like it's one really simple thing why I got to do it like this, but we're going to make a claim about mu, and we're going to ask that the data that we collect, did that provide evidence against it? Right? Because that's like me going downstairs and shooting and making a fool. The data gave me evidence against my claim, right? So you didn't believe my claim anymore, you believe something else, correct? What happens if I don't find evidence against it? That's like going downstairs and me making 15 out of 20. The data is consistent with the claim, yes? See, there's these two outcomes that can happen here. All right? Let's continue. Now, I'm going to be honest with you. In a test of significance, there's always two claims to be made about your population parameter. There's the one that we're seeking evidence against, and there's the one we're seeking evidence for. So, the question says that we seek evidence for a loss of sweetness. How do I know that that's what I want? Are these data good evidence for cold loss of sweetness in stories? That's what you're seeking evidence for, a loss of sweetness. In terms of mu, you are seeking evidence that mu is greater than 0. Remember, on the average, people would score it higher before than after. We're seeking evidence of a loss of sweetness. We're seeking evidence that mu is actually greater than 0. Where does that come from? That comes from the question. Okay? Now, the claim we test. The claim we test, we assume to be true. Is no loss of sweetness. Okay, in terms of mu, no loss of sweetness means, hell, if I scored it a 6, it's set in the room for high temperature for a month, I would score it a 6 again, right? The cola tasted exactly the same before as it did after. In other words, in terms of mu, now, my statistician friends hate me for this next little thing I'm going to circle. The reason I have to work at this ass backwards is because of that equal sign right there. The claim that we're going to test, that we assume to be true, is no loss of sweetness. The cola tasted exactly the same before as it did after, right? After as it did before. Okay? So, a couple of thoughts with that little thing I have circled there. See, if that's the one we're seeking evidence for, mu is greater than 0, what are we seeking evidence against? I'm seeking evidence against that. Because if I find it, then I have evidence for the one that's on the top of the page. Now, we'll talk some more about this language in a moment. My first thought is this. If mu is equal to 0, you see this line right here? The claim that we assume to be true no loss of sweetness, that mu is equal to 0. That's what I'm doing right here. I'm going to assume mu is equal to 0. Then what I know is the sampling distribution that we have looked at before of your sample mean, of your sample statistic, x bar, we know it's going to be normal. Why? The second condition says the population distribution is normal. That sampling distribution is going to be normal. It's going to be centered. I'm going to write it down like this first. That's the one we used in chapter 13, 12, 15. I know it's going to be normal. I know it's going to be centered at 0. Where does sigma come from? That's your third condition. Where does 10 come from? That is your sample size n. We took an average over 10. And so we pull the calculator out, and I'm normal, and I'm centered at 0, and my standard deviation is 0.316. We okay? Right? So sigma was given to me. I'm looking at a sample of size 10. The 0's coming from right there. That's why there's a 0 there, why there's a 0 there. So what this is telling me is that sampling distribution looks like this. There's your normal distribution centered at 0, a standard deviation of 0.316. All right, that's what it looks like. Now, there's nothing new there. Me and you've talked about that all kinds of times, right? But the catch is 2. X bar was 0.3 for our 10 trained tasters in that example. We okay? Now, if I draw you that normal distribution again, yeah, I'm going to label it for you again. And I put 0.3 on here. How far away is it? Is it very far away from the center? Is it very far out the tail? Is 0.3 really that far away from 0? Now look, when I'm asking you that kind of shit, I know I'm looking at 0, and I know x bar is 0.3, and 0.3 is 0.3 away from 0, right? What I'm asking you is how many standard deviations away is it? In other words, is it a long way away from the center in terms of the number of standard deviations away? The answer is no. The standard deviation is 0.316. 0.3 is what less than 1 standard deviation to the right of the mean, right? You're not very far away from the center. In other words, that picture there is like us going downstairs and me making 15 when you're expecting me to make 16. You didn't find anything. In other words, x bar being 0.3, not being very far out the tail, being close to the center, being within 1 standard deviation of the center, x bar equals 0.3 is not evidence against mu being 0. X bar equals 0.3 is not evidence for mu being greater than 0. Now, I'm going to do this. What does mu being 0 mean? No loss of sweetness. What is mu being bigger than 0? A loss of sweetness. We were looking for evidence of a loss of sweetness, and we failed to find it. The data is consistent with mu being 0. The data is consistent with no loss of sweetness in the bowl. 0.3 is not far enough out the tail to say there's something up. It's like shooting the foul shots and me making 15 or 14. I'm very close to what you're expecting. You didn't find anything. Okay? I got to give you a number 3 here, and I'm going to skip over, and I'm going to look at example 17.3. They do the same experiment again. N is equal to 10. They get a different X bar. X bar this time turns out to be 1.02. Not 0.3. X bar is 1.02. So on the average, those 10 trained tasters thought it lost at least, on the average, 1 point of sweetness being in storage. Okay? Everything is exactly the same. The only thing that's changed is you got a different sample size 10, you got a different X bar. You have the same sampling distribution centered at the same spot with the same standard deviation. How far out the tail was 1.02? Yeah, I know. Just looking at it here, hell, 1.02 is only 1.02 points to the right of 0, yes? How many standard deviations to the right is it? Oh, shit. X bar equals 1.02 is more than 3 standard deviations to the right of mu equals 0. In other words, an X bar being 1.02 is very unlikely to happen by chance if mu is actually equal to 0. An X bar being 1.02 is very unlikely to happen if the cola is not losing sweetness in storage. This is like going downstairs and shooting the foul shots and me making 4 or 3 or 5 or something else. In other words, here you got good evidence. Against mu being equal to 0. No loss of sweetness. Actually, there's so much that you believe something is up. You have good evidence for mu being greater than 0. Loss of sweetness. All right, you see which direction this is? I'm letting you write this, but you see here? That's to the right of the mean, right? To the right of the mean is where mu is bigger than 0, yes? 1.02 is so far out the table. And it's so unlikely to happen by chance. Something has to be up. And what has to be up? This distribution can't be centered at 0. It's got to be centered something to the right of 0. Anything to the right of 0 is where the cola is going to lose sweetness. Because did this value actually happen? Damn straight, they had 10 frame tasters. I got an X bar being 1.02. It actually happened. But if mu is equal to 0, it's so unlikely to happen, something's got to be wrong. And the only thing that can be wrong is that sampling distribution is not centered at 0. It's centered something greater than 0. If it's centered at something greater than 0, then 1.02 is not so far out the table. This is the two sides of this test of significance, right? Point 3, hell, you're within 1 standard deviation of the center. You didn't find anything. The data is consistent with the claim you were made to be true. 1.02 is so far out the tail, more than 3 standard deviations away. What's wrong? you can't be centered there. You got to be centered somewhere to the right. So then you're not so far out the tail because 1.02 actually happened. This is the one we're always looking at for evidence for, right? We're always wanting to know, okay, you're not here. You're over here somewhere. Now, I can't tell you if x bar is 1.02 what mu should be. I mean, I can't tell if it should be 0.6, 0.7. What I can tell you is it ain't 0. Because let me ask you this. Anybody remember the 68, 95, 99.7 rule? Within 3 standard deviations of the mean, what percentage fall there? 99.7%. Yes? That x bar being 1.02 is one of the 0.3% of all of them that would be more than 3 standard deviations away. How likely is it to do this and get a 1.02 if mu is really centered at 0 and you're outside that 99.7? Folks, it never freaking happened. There's no way you're centered at 0 and you're getting one of the 0.3%. Ain't no way in hell. What's wrong? Well, no, you're not centered at 0. You're centered somewhere over here. Now you're not so far away. That one, I know, I keep going over and over because this is it. The calculation is no big deal. We've done the calculation already. The calculation I'm going to show you. Here, well, hell, one standard deviation on either side has got 68%. 0.3 is one of the 68%. Well, hell, that's not unlikely. That's actually very likely to happen if you're centered at 0, yes? So, I always think about how far out the tail you are. The further you are out the tail, the more evidence I got against where you're telling me you're centered, the claim you make. And more evidence in favor of the thing you were actually asking me about to start with. All right? Now, if I can get you to have a halfway thought about this one, that one, what's the difference, how far out the tail you are, the only thing me and you have left to do is we need to do each little part. As I told you, there's like 4 little steps here to get the whole thing done and what calculation I need and draw my conclusion and all that kind of stuff. So, where we start is here. Okay? And the starting point is no calculations, no nothing, stating hypotheses. Now, we should be able to state the hypotheses whether I can do any calculations, draw any conclusions, or anything. All right? Now, here's the thing. Always 2 claims about, I'm going to give it to you in general, about a parameter. There's always 2. Every test that we do, there's always 2 hypotheses, and all the hypotheses are, these are very, careful statements about the claims about our population parameter. In this chapter, it is claims about mu. All right? Now, I'm going to do it like this. I'm going to number them. There's 2. One of them is called the Null Hypothesis. It's denoted H subscripted with a 0. And unfortunately, I don't always read it H subscripted with a 0. I read that as H naught. I mean, I would give you the Beverly Hillbillies reference, but you guys all look like me, like, who are you talking about? That's H sub naught. That's H subscripted with a 0. That's the notation for the Null Hypothesis. Now, what is the Null Hypothesis? I'm going to give you some statements here. What is the Null Hypothesis, right? It is the statement of no effect, or if you like, no difference. I could also say it's a statement of what's the norm, what's the status quo, what's been happening. It's a statement of, I can't tell you what the number is. It's a statement, it's a claim, it's a hypothesis that mu is equal to some value. I'm going to put you a little question mark here. I don't know. It'll come from the problem what mu is equal to. 3. It's the statement or the claim or the hypothesis. I'm going to use claim here. It's the claim we assume to be true. It gets us started. It's the claim of where the sampling distribution is centered. If it's a claim of mu equals something, well, then your sampling distribution is going to be centered at whatever that mu is. If mu is 20, if mu is 72, mu is 3,000, it's telling you where that sampling distribution is centered. 5. It's the claim we seek evidence against. I don't know how many other things I can tell you. Everything I can think of, I just told you about what the null is, right? It's this claim of no effect, no difference. What's the status quo? It's a claim that mu is equal to some value. It's the claim we assume to be true. It's the claim of, okay, where's the sampling distribution we're looking at centered? It's the claim we seek evidence against. Well, then there's the other side of the null hypothesis, and the other hypothesis or claim or statement is called the alternative hypothesis. It's denoted by a capital H subscripted with an A. That's the alternative. Now, I don't have near as many things to write down about, okay, so what is the alternative? The alternative, to be honest with you, is the claim or the statement, the hypothesis. It's the claim we seek evidence for. How about this? It's the claim that shows up in the question in the problem. It's the claim that we're willing to accept to be true if we don't believe the null. How's that? So the null is a statement about, a claim about where you're centered. The alternative is going to pick a side or maybe not pick a side. See, the thing is this. I only got one thing to say, right? The alternative is denoted by that. It's the claim we seek evidence for. There are a one-sided alternative. You pick a direction. In other words, I'm going to do it like this. It's either mu is less than some number or mu is greater than some number. You pick the side, right? The first one I would be saying, okay, it's a one-sided alternative to the low side, to the left, smaller than mu. The one on the right there is, okay, it's a one-sided alternative and it's mu is greater than some value. Or it's a two-sided alternative. Nobody forced me to pick a side. Now, there's no coincidence that I'm using question marks here and a question mark in number 2. Because whatever value goes there, whatever mu is equal to in the null, whatever kind of alternative you have, mu is less than that value, mu is greater than that value, one-sided, or mu is not equal to that value, that's the exact same value. So whatever value for mu that shows up in the null also shows up in the alternative. Okay? Now, the problem we just did, the one about the colas, what was example 17.2? If I was to use this notation, oh, time to go home. Can I get the notation out? The null would have been, that's a template. The alternative would have been, there's three pieces to be filled in, right? There's the value, and then there's the sign that's got to show up in the alternative. Well, remember, we were seeking evidence of a loss of sweetness, and we decided that those should have been 0, and we had loss of sweetness was that mu was greater than 0. Remember, an average of 1 meant that we lost sweetness. We scored higher before than we did after. That's the notation. That's the way you write that. Those are, right? H naught, mu is equal to 0. H subscript to the A. Alternative, mu was greater than 0. When we come back on Tuesday, I don't want you to think every time I do this there's zeros. We're going to look at some of the other problems here and pull out different numbers and make sure that we can write the alternative, right? Be careful going to the house. Get your test answer sheet back. We posted it, streamers, all that. I'll be sending them to you when I get upstairs. Be careful. We'll see you on Tuesday.